He works in the Institute of Cybernetics. Yes, you can start.
Yes. Good evening, everybody. So my talk will be about a paper which we published back in days 5 or 6 years ago, which is dealing with practical applications of radars in well, pretty much practical scenarios, which I will describe later. So when I was preparing this talk, I um, I was choosing between making it very technical with lots of formulas, or just describe the history behind the project and what we have done. And I decided in favor of the later. So the paper which I will be talking about is this motion zone estimation for adaptive radar system parameter selection. So the work have been done while I was head of research at a Ring company, which at that time already was a part of Amazon. So what is Ring, and what did they do? What was their business, and what was my uh, um, impact on this business? Ring produces security cameras for your home, and there is a very large selection of these devices, and they produce them probably for 10 years already, or something like that. And they grew from a small startup up to the multinational company, and Ukraine was one of the scientific bases of this company. And there are a lot of problems uh, with security cameras, which, well, different interesting scientific problems which you can solve. One of them, how does this thing work? So the camera should somehow detect that you approach the door, or the Americans live in one-story buildings, unlike Europeans mostly. So they want the camera to detect the movement in the sidewalk or the front yard in front of the camera, up to probably 15 meters or 10 meters or 12 meters or something like that. And then they want the camera to classify the movement. Is it a person? Is it a car? Or is it just an animal, like, I don't know, elk or dog or cat or zebra or whatever? So there are a lot of funny videos with different animals crossing the view of the camera. And at the same time, there are, well, Americans have these privacy concerns, and they are very problematic to deal with. The privacy is when you are recording the video, and there's some person who doesn't want you to take the picture or video of themselves on your camera. And one of the triggers which started this project was a lawsuit or in Chicago in somewhere in 2018, 2019. And one woman sued the Ring camera owner that she was captured in the camera view while she was very far from camera, from this, she in front of camera, but on the other side of the street, and somehow the video leaked into the internet, and she was very angry about it. And our management leadership decided, you guys need to invent something, add something to the camera, so the camera would know the exact position of the person if this person is approaching the front door of the homeowner, or is it person just passing by. And another problem, for example, if we have a computer vision in this camera, and they already do have this, so there are two problems with computer vision. First, camera doesn't know the distance, so camera only measures angles, and you can only guess the distance to the person, which you are, if you even detect the person, from your camera, based on average height of the person, and then bounding box, which you detect with some kind of neural network. The problem with detecting via computer vision is a low distance the large error of distance estimation. First, second one, if you are doing it on a cloud, in a cloud, send the video somewhere, and the cloud processes this video and then gives you estimate. There are a lot of time delays. The cloud processing is expensive, especially when you have tens of millions of these cameras installed everywhere, and several of them in a single homeowner may have several of them on the front yard, on the backyard, whatever. If you do processing on the device, the usually neural network is reduced, and the quality of this estimation is much less, even worse than in the cloud, and also it takes a lot of energy, and you cannot do it on a battery powered device. So you need a device which is connected to to the power supply, which is not always available. So we need invent something. What are the ways to estimate the motion? For example, PIR sensor. Well, I'm describing everything assuming that you guys know nothing. So if you know that, just please let me know. I will skip it. So PIR is a passive infrared sensor. You may see them. They look like this on the left. They have a semi-transparent window, which consists of Fresnel lens. Fresnel lens projects the output space, outside space, into these two sensors, which compute difference in the flux, in the thermal flux coming into the sensor. And when you move from one zone of the sensor to a different zone, then you see this spike of positive and negative spike on the PIR sensor. The zone might be the PIR might divide the space into vertical and horizontal zones, and they are very crude. So you cannot correctly estimate a person moving near the camera and a car moving on the street. So both will probably give you the same output in terms of the signal here on the bottom right, and both of them might trigger the alarm, and then camera goes on, and then computer vision starts. It consumes a lot of energy. It might give you false alarm to your application, to your phone, and it will distract you, and then you switch it off, and then you will never use it, and just nuisance when every car coming past your home triggers a false alarm. Actually, Ring cameras are equipped with 1 or 2 or 3 PIR sensors, and we even were able to estimate the distance to the moving object, but it's difficult, and PIR may also be triggered when the sun is going out of clouds or going back with like covered with clouds, and this flux of thermal energy will trigger this PIR sensor, which is not very reliable, not very accurate, but it's cheap and it's very energy efficient because it never sends any signal. But our management decided that, well, we are a technological company. Let's add some magic, modern magic to the camera, and let's try to install a radar. Okay, so a little bit about the radars. If we install a pulse radar, which transmits a short pulse to detect the object, then the radar equation looks like this. We have a PR is a received power. It's from a power received perspective is very bad for very bad with distance at which we want to detect the object, because the power will be will decrease as a force as r to the force, which with r is a distance to the object. PT is a power transmit, g is a antenna gain, which might be the same antenna, which might be different antenna. Lambda is a wavelength of this signal. Sigma is a radar cross section of the target, and we estimate the distance to the target by measuring the time of outcoming and incoming pulses, transmitted and received pulses. We estimate the distance to the target. The problem with this approach, there are a lot of problems. First, we transmit only short pulses, meaning average energy is only a fraction of total energy which we send, and also we need as a result we need high peak power. The good side is we can have a long range, but the downsides are low range resolution and the blind spot near the radar, where static clutter, where very short time difference between transmitted and received pulses will not be we will not be able to detect this time difference. And the blind spot is the main problem for our application when we have a couple of meters, maybe 10 meters, 15 meters of the target, which may be a human, maybe a car or whatever. So we need to use a different approach. And the different approach is frequency modulation continuous wave radar. So how does it work? It sends a continuous wave, but it changes the frequency of this output signal. It is just a sinusoid, the signal, but the frequency of the signal, let's let us have it in red. So the transmitted signal is red. The signal frequency is changing with time with this zigzag pattern. When we transmit, then after the signal is received, it will be received with a time delay, and we will receive a frequency which was previously we transmitted delta t time before that. So we know this delta f frequency difference at the time when we receive it, and this delta f corresponds to the range at which we detect the target. And the advantage is also we can have several delta f frequencies, meaning at the same azimuth we can detect several several targets. So the mathematics behind it is not quite complicated, but I will not put it here because it's not about talking about the frequency modulation continuous wave radar system as a whole, but just to illustrate. And I would like to point out this wonderful YouTube channel which describes it in very nice infographics for someone who is interested to understand how it works, and why FMCW radars are so widespread now, and have a lot of applications in automotive, in security, in industrial. So it's a very if you would like to know better and see for yourself how it works and what mathematics is behind it, I just encourage you to look through a couple of videos. They're quite short. And also, if you would like to show your students, there are Python notebooks and examples and some training material in the description of the video. So please check this out. At that moment, it was 2018, 2019, when I was leading this project. There was several radar development boards available. Now there are more boards, but at that time there was very few of them. But we chose this Texas Instruments industrial radar. It has four receiving antennas, 3 transmitting antennas, and it, in theory, allowed you to estimate, to get a 3D model of the surrounding area. Well, at least they advertised it as such. It has the 60 to 64 gigahertz transmitting frequency. It has digital signal processing power on chip, and this board was quite large, like a palm of your hand, something like that. And we were using this board. And how did we collect the data? Let me talk about that for a moment. So we had a radar put at some for example, we were testing it in a scenario when a person approaching the radar, meaning your home, and we had a private home, a front porch where this radar is installed, and also empty space like a parking lot with no cars, no people, nobody, with painted semi circles and radius over the place where we were gathering the data. And there were actors doing the task of going around the circles or approaching from different angles, or just walking, simulating the sidewalk as person just passing by, a car passing by, etc. And we were gathering the data with different tilts of the radar. So the radar is not just perpendicular to the ground, but it is located at some angle, 15, 30, 45 degrees angle on a different height. And our task was to gather realistic data from in realistic scenarios, and to remove as much noise as we could from static metal objects which were emitting the most energy back. It might be fans, it might be some doors, some cars, which are parked cars, any other objects, light stand, whatever. They were creating a lot of noise. It might be also bushes, which or leaves of a tree, which at this 64 gigahertz are very well visible in the radar as a moving object standing in the corner of your yard. And the problem was with such sophisticated radar, which is able to detect these objects like leaves and metal poles, cars, etc. You need to distinguish between these two types of points and separate the points which are which belong to the human, not just human, but the human which is approaching your door, which might be a courier with a package, or might be a thief, or might be some threat, or some neighbor which would like to call you. So we were gathering this data, and while we were doing it, we decided to find the best parameters for the setup in which we are gathering the data, and the parameters of the radar itself. So the radar can be tuned, and this chirp which radar uses, you can tune for example, you can slightly tune the frequencies at which it works. You can tune the slope of this chirp, how fast the frequency changes, and how long does it goes. So we applied semi-automatic chirp parameter tuning to find the best parameters for the chirp itself in particular scenario which this radar is installed. And then
what is chirp? Chirp.
Okay. Once again, chirp is this triangular shape. So you may want to choose the chirp itself, depending on which parameters you would like to estimate best. Like, do you want to have to detect objects with large velocity or not? Do you want to estimate the range best? So this is the parameters of the chirp itself. So the slope at which the height of this chirp represents the range, maximum range. But the slope will give you the range resolution. So are you able to distinguish between two objects which are located on a very uh, which are located close one to another? Are there two humans or a single person like this? Or two cars or a single car at some azimuth. So this is the chirp parameters, and you can at this this radar allows you to choose the different chirp parameters depending on your application. It was originally designed for the automotive setup, where you have a radar hiding behind your car radiator in front of a car, and this radar allows you to detect a car which is in front of you, moving in front of you, and if the radar detects that distance between you is less than it's set up to be, or the car is approaching you, then your car may slow down, or it may stop even automatically even if you didn't do anything. So the modern car can often use this radar technology, and Texas presented us with several development boards which were like originated from automotive setup usually, but the problem with automotive, you have a large metal object on almost empty road. This is a basic scenario, and you almost always sure that there are no large metal objects in between you and the car which you are tracking. And the large metal object, a car, has a large radar cross section, so a lot of energy from emitting from your radar goes back, and so the signal to noise ratio was very good. But when we have a human, depending of the weather, depending on the clothes which the person is wearing, then there are different levels of transmitted energy which goes back, and you cannot detect the human below 15 or maybe 20 meters with this kind of radar, and that was a problem by itself. Okay, so radar, this radar particularly to detect the velocity of this point, it was using several chirps in a row, and then it was grouping. Well, at least it was the idea was is to group a point into a trajectory and then estimate the velocity. And well, if you have velocity, if you have a range, you have distance, and then well, you know where this trajectory is going. And so we applied Kalman filter to group the points in the trajectory. We then see which points are not moving. We remove them at all. And these are static points which usually correspond to your surroundings, like any metal objects which are presented, which are present in any practical scene. And also we remove oscillating objects like, for example, fan blades. If you have somewhere a fan, or you have leaves, you have a bush, and any slight wind will move the leaves, and then you have to remove them. Otherwise, you just have a large moving object, and it will trigger alarm every time. So what about the tuning? Somehow we usually we read from left to right, but somehow in this paper we put wrong parameters to the right and the proper parameters on the left. But okay, so when we choose a wrong parameters for the chirp, and we decide in favor of velocity resolution, then we might end up with the ghost points. So what are the ghost points? If for example there is a range like 20 meters of the radar, and you set up your chirp for 20 meters, but there is an object at 25 meters, and this object has a quite large radar cross section, so the radar signal will bounce back to you. Then if we look at this chirp, it just repeats itself every several like every time it repeats itself. So you will not be able to distinguish the signal which came from one chirp to another chirp. And the signal from a adjacent chirp, it has less amplitude, but we don't care about amplitude at all. We care only about frequency in this estimation. So if you have an object, if you have a range of 20 meters and you have an object in 25 meters, this is the same as object at 5 meters. So you cannot distinguish between them. The same goes about velocity. If you have a velocity resolution, maximum velocity like 10 meters, and the object is moving at 15 meters, it is the same object as 5 meters per second. So we were able, it's like a trial and error and some kind of guessing game of this approach. But if you look at the image on the left and image on the right, they are represented by a single repetitive movement of the object. So what did we do? How do I explain it? We had a small car, which is like I don't know, it's like a vacuum cleaner, you know, automatic, like Roomba. But it was programmed to move with the same speed, by the same trajectory, in a hangar, quite large hangar. So there are no other objects moving. And on top of this car, we have a plastic human body, like mannequin, which you put the clothes on in just from a clothes like shop, just plastic human body. And this car is moving towards or from the camera or to the camera or radar or whatever. And it performs the same task for different chirp parameters. And our approach, knowing that the only single object is moving, we were able to find the parameters which are the best for this surrounding setup, and which are best detect a single object trajectory. And you may see that the same objects moving on the left, it's detected quite nicely with very little noise, except for the I don't know why. Maybe because it was a plastic model with arms spread to the left and right, and probably you see it. It's not very clear at less than 5 meters. But on a distance up to 25 meters, the object is quite nicely represented, both in angle um, and distance. But if you look at the right picture, there are like two objects moving at the same time. It's a like ghost object, which is a disadvantage of a frequency modulation continuous wave radar, which unfortunately gives you this ghost images beyond the range, both in velocity and distance. So if the object is moving far enough, or if it's moving faster than you expect, then it might be represented by a false point, a ghost point like this. And there are a lot of another picture. So on the left, we have an object, the same mannequin moving at 20 meters range. Imagine you are at the front porch, 0 point, and 20 meters is your sidewalk near your house. And a person is just loitering at this sidewalk back and forth and expecting for a taxi, whatever. So they are moving back and forth. And on the left, on the left picture, we have a quite nice estimation of the person movement. But on the right picture, before we estimated the good parameters of this chirp setup of the radar, it was very chaotic, and you cannot understand that the person is just moving on a sidewalk. You may understand that it's already on your front yard and just approaching your camera. And another one, the movement like from a side, back or forth, it also presents a lot of challenges if the maximum velocity was not properly set. So the maximum velocity here should be 15 meters, but if you choose it 5 meters, 5 times less, then you have a lot of ghost data which produces, which your camera will only understand what's going on. Okay, so we also tried to remove static objects. So how to read this image from this this slide? We have a radar which is perpendicular to the ground, and it's located on some distance, like 1.5 or 2 meters or 2.5 meters over the ground. The ground is flat, and the person is going by this 8 or glass by this 8 shape. And left column is a bird's view. We are looking from above. And the second column, we are looking from a side. So the first column is XY coordinates. And the second column of this graph, this is when we look from Y and Z. So there are a lot of clutter, which are static objects, which we have to remove. They may be represented by some absolutely false data. And the third column is when we remove the static objects. You may also notice that the points in the point cloud are have this they are not they spread evenly. That's because we have some angle resolution which is far worse than 1 degree. It's quite bad actually with in this radar setup. But well, at least we have this data, and it's a magic that it actually worked. No one expected this picture. And so when we estimate the static points, we can even estimate where the ground is, where is the ground level. And on the right column, the last fourth column, green level is the how do we estimate the ground level. So, how the angle between green and blue estimates how do we think the ground is located. Where is the ground? Are we tilted, or are we pointing straight parallel to the ground? And we see that quite a lot of points, like in this graph on the bottom right, there are a lot of red points which are static. We remove them in this with this method. We remove them, and we know that this area is not where we can expect any visitor to come. So even if we don't know that camera doesn't know the angle, and the user may put the camera at any angle with no regard to the user manual, we still can somehow estimate the angle at which we are looking at the space, and we can then understand which points might actually represent a human approach in us. So if we are looking at the right column, the blue line is what we think is parallel to the ground. And well, actually, the top and bottom are quite nice, with middle image. Yes, it has a angle 2.6 degrees instead of 0, which is still was far beyond our expectations. I want to show another test result. So we tilted the radar 30 degrees to the ground, so it's tilted forward, and we again collect the same data. Person is moving this shape, or I don't remember, maybe person, maybe it was a plastic body double moving this shape. Yeah, don't remember, and all the images unfortunately are not under NDA. I cannot show them. So, and we gather this data. So again, from first column, we are looking from above, bird's eye view. The person is moving at this 8 shape. The view from a side, we have a tilted point cloud, and when we remove the noise, which is when we tilt it, it's becomes more difficult problem. So less of the noise is removed, and we see that the estimated angle is 32.2 degrees, but we know the angle was 30 degrees, which is quite good by itself. It's not a big deal, and it allows us to understand where is the person and the height of the person, because we have three-dimensional data, and you can see the height from the ground was, if you look at the description of the picture, was 1.5 to 2.5 meters, and this allows us to understand if this is a person or this is a small animal, and we can just skip it. Don't turn on the camera. As we know the angle, the distance from ground, and then we can estimate the point cloud representing is it a human. Okay, so this is a table of results. You can see the ground truth data on the left. So 0 is perpendicular to the ground, 15, 30, 45 degrees is when radar was tilted forward. And then you may see the height, estimated height of radar. The difference is quite large, so it doesn't perform very well. We cannot estimate the height accurately. We fail like maybe twice, two times worse than we should. But angle of tilt of the radar is quite accurate, even for this small radar which we have. Yeah, and the problem with this approach was that a practical problem. It was that this radar it is manufactured out of very expensive material. This white material is called Rogers. It's something like ceramic. It's not a regular PCB. It's a very expensive material, and our management decided that the research is very important, very nice, but they decided to go with much cheaper Japanese Infineon radars, which were much more primitive, and but they allow to put all the radar inside a chip itself, and no external components like antennas or expensive materials, expensive substrate to put this chip on were not required. And these radars from Infineon were much worse in terms of performance. So the unlike this nice point cloud which we can see here, so and I still think it's a very nice point cloud from a radar. The angle of we estimate the angle of from this Infineon radars, and the angle error sometimes exceeded 40 degrees. But nevertheless, it was a management decision to go with this radar, and now Ring cameras have something like these radars instead of the Texas which we were researching. And only what is left from this research is the papers which we made, but it unfortunately never materialized in a product. But well, it was fun at least. Probably that's all. But anyway, I'm looking forward to answering your questions.
Thank you for your talk, and any questions, remarks? And what was the outcome of your research?
Yeah, as I already told you, the outcome should have been like this. So we have a camera, and it's when you equip it with radar, it should give you much better precision recall from a point of view. If is it a person approaching you? Is it a courier which is placing a box on your front porch, or is it a person just moving past your home, and we don't have to trigger the computer vision, drain battery, ping the user of this camera that someone is going uh, to his front porch, or car is parking into his driveway or something. So that was a whole idea. Just let's equip our camera with powerful radar, which can distinguish between several practical scenarios of passing by, vehicle approaching, animal, and etc. So yeah, it actually these cameras, some of them are equipped with this sort of radar, but unfortunately not the type which we were researching, and uh, so big chunk of this research is not applicable for this radar which is used, because it's not 3D, it's just a Doppler radar with some, yes, maybe FMCW as well, but much more primitive, and it doesn't have this this powerful digital signal processing as Texas. And yeah, it's a pity that they don't have it. Otherwise that would allow to estimate, well, crudely, but still estimate the 3D model of surroundings, and then cancel some of the areas which clearly represent bushes, trees, or metal objects which will not which will not produce as a human moving to you. But yeah, still it's interesting. Um, as a part of research, we were visiting this company in Israel called VR. It's old Hebrew for vision. So they were using at that time, 6 years or 7 years ago, they were using 70 to 80 gigahertz radars as a way to understand if the person for example, children inside the car, if there are children inside the car, if there are person lying on the bed, or person is on the floor, is this person standing or is it moving, is it breathing? Because at these frequencies you can detect even slight movement of your chest, which is heartbeat. You can see the smallest movement of skin. So yeah, it's able to detect humans, but unfortunately, on a outdoor, they failed miserably, and that's why we choose Texas, for example. So the technology is amazing and wonderful in closed space, but not an outside world, and it's very expensive for this $300-400 camera to install. But well, the the videos of them and watching the output of the radar is some magic. Can see through walls, can see through drywall and some plastic. Yeah, this radars they produce are amazing, but not for this job which we had.
Any more questions? And from statistical point of view, it is a kind of pattern recognition.
Yes,
You
yes,
have several possible scenarios. For example, animals. You have typical movements of cat or a dog or a
yes,
deer or whatever, or squirrel, and you can recognize what animal moves, or at least you have several possible scenarios and you analyze, and then you make a decision. Either you decide which object you observe, or otherwise you continue observations till you are able to decide. Or
yes, yes. And the radar is very good at detecting objects at night where usual cameras fail. So you don't need night vision cameras or thermal cameras. Thermal cameras actually is very expensive. So radar is much more cheaper than thermal camera, and radar is able to work at night in a fog, in slight mist, but it's when it's raining, then the radars usually fail. But at least at night, in fog, in some smoke, they will work well. This 3D radar will detect a small animal like dog or cat with no problem. It was able to detect like this robot vacuum cleaner without plastic body, human body on top of it. No problem. So if it's a like dog-sized animal, it will detect it. And the deer and elk and larger animals uh, are visible as well. But the problem with the radars, moving nuisance, moving objects, this is a large problem. You have to adapt and somehow to remove them from this scene, especially when you have a realistic scenario when you have a lot of objects in on your front in front of this radar, not just empty asphalt pavement, and that's it. If you have objects standing line, trees, bushes, that's a nightmare for this radar. It will output a huge point cloud. And the scene which you see here will be packed with so many points. So it's you need to remove like half of them to at least see anything useful.
and in Ukraine, is it popular, or do we have in Ukraine such radar systems installed or not?
Yes, well, anyone can buy the ring camera with radar. They are available, but again, they unfortunately don't use a 3D radar. At least, well, I was I was head of research there before the full scale, but after full scale, I have no idea what's going on there. I left. So at least they used more simpler radar, which can detect movement and estimate the angle of approach, but it's far worse than what we see in this picture. But this technology can be further developed. The radars which Texas offers now are much more smaller, and instead of this large and totally totally difficult to work with the board, they offer antenna on package. When this antennas, the bottom right corner is antenna array. They moved everything to this black microchip, and you just install the chip and you connect some wires, and then you can control the radar and you can gather the data and use it for any type of application, like military, like industrial, counting objects, for example, in a conveyor belt. With no other cameras or computer vision, you just can count with radar. Automotive, you can prevent frontal damage to your car by just braking or keeping the distance between your car and the car in front of you. When the car accelerates, you just follow the car in front of you, etc. So there are such applications, and the radar applications are very good at, for example, in hospital scenarios. When you have a person in a hospital room, and this person may be sick, and this person may lose conscience for some reason, and this person doesn't want anyone looking at them while being in this room, the hospital room, for obvious reasons. They may be naked. But such radar, 3D radar, will easily distinguish between a person sitting on a bed, lying on a bed, or lying on the floor. And then call a supervisor, call the nurse to check if this person is okay, or maybe it just felt bad and they are lying on a floor and they just feel badly and they need the emergency procedures.
So the distance estimation is more reliable compared with angle estimation.
Yes, distance estimation is much better than angle, especially when you have very little antenna array. Like if you have one transmitting, one receiving antenna, in fact, you only have distance estimation and velocity estimation by Doppler shift. Or maybe you send several pulses, you have several distances of the same point, and you decide, okay, this point moved. You need at least two antennas to detect angle, and then you still have very bad results, especially when the object is moving not perpendicular to your radar. When the object is coming on the edge of your field of view of your antenna array, then the results are completely very bad. So our practical results were like 40 degrees of angle error for a person on an empty parking lot. No other objects moving. Everyone is hiding somewhere behind the scene on the background, and the person is moving towards the camera, but not perpendicular, but from a side. like an angle about like 45 degrees, and the points estimated are just something like plus or minus 40 or 35. So the radars, at least simple radars, are very bad at estimating angle, especially on the edge of this field of view.
But you speak about two coordinates, and we have movement in 3 dimensions. Imagine that you are interested in height of your object and how to deal with the third coordinate.
This radar is able to detect it in 3 dimensions. You see there are 3 transmitting antennas, and one is slightly above another. So on the bottom of this board, you see 3 antennas. One in the middle is a little bit to the right. So they are shifted in space. And this is how they estimate Z coordinate. But actually, the Z coordinate is worse. Even X and Y are more or less okay, but Z coordinate is has very large error. At least in our experiments, we were not very happy with it. But well, it was like 6 or 7 years ago. Maybe since that time, Texas made improvements of the radar technology, and that's improved. And maybe they have a larger if they have for example Voyar, they had a lot of antennas, and they were able to estimate in 3 dimensions and quite accurately. So they could see a pipe like maybe 10 millimeters thick pipe, metal pipe, behind the drywall, 40 centimeters from a drywall. So they can see through the walls. And the position of the pipe was extremely accurate, up to some millimeters in 3 dimensions. Not just in 2, but in 3 dimensions. But they were using like, I don't know, 40 or 70 antennas array. That's a lot of power on a digital signal processing part to have much more than Texas offered, and we were not able to enjoy this, unfortunately. And yeah, but the technology is available.
Okay, if there is no questions, then thank again for your interesting talk. And I want to make an announcement that now I am a member of editorial board of Ukrainian Mathematical Journal. And I am a member of team responsible for probability theory and mathematical statistics. And Ukrainian version of this journal is published in Institute of Mathematics of National Academy of Science, and then Springer publishes English version of this journal, and the journal is indexed in Scopus and Web of Science, and it is Q3 journal. It belongs to the third quartile. And you are welcome to submit your papers to Ukrainian Mathematical Journal, at least to support Ukraine in such situations. And so we will have a break till September. I hope we will resume our meetings in September. And you're welcome to send me your proposals for talks. and then we will make a schedule maybe from September till December for that period. Okay. Thank you for attending our meetings, and goodbye then.
Yeah, goodbye.
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 Goodbye.